In our lab, we're going to be measuring Boyles Law. And so when you click over to LabFlow, I want to remind you first that the very first thing you'll see in LabFlow is the PDF, and you must read this. This is going to give you all kinds of information for every single lab that we do, but in particular for this lab, it provides a lot of information that you need. So it explains Boyle's Law here that as long as the temperature and the amount of gas remain constant, P times V is a constant. Okay, so we're going to test it. The way that we're going to test it is using a device like this, which is just a simple syringe set to a given value. In this case, we start it with a value of 5 milliliters. And essentially what we're doing here is we're hanging weights from it to further compress that gas inside the syringe. And we know based on Boyle's Law, as the pressure increases, right, we're pushing harder on that syringe, the volume inside is going to get smaller, right? Likewise, if we pull away from the syringe, if we try to pull the plunger out of a closed syringe, the volume will increase, but the pressure inside will be decreased because there's this inverse relationship. If P times V is a constant, then anytime pressure goes up, volume must come down to compensate, and vice versa. So they go through in this PDF the description of what's happening, how this would work if you were doing it in person. They show you the setup here with a little clamp, and then they explain what's going on. Now, essentially what we're doing, if you read through all of this, is that you're doing, right here, 5 measurements by adding weight to the top of the syringe. So 5 measurements where we're adding pressure to the syringe, decreasing its volume. And then we flip the syringe over so that it's now hanging upside down. And now when we hang the weights from it, we're pulling that syringe open. So 5 measurements with increasing volumes. And the reason I'm pointing this out is because we have to do the math a little bit differently. So I'll show you that in a second. You're then going to go through and calculate PV values. And so we have to calculate pressure first. Pressure is the amount of force exerted on an area. So you may be familiar in common usage with the pressure unit of pounds per square inch, or PSI. That's what most people think about when they're filling up the tires on a car or something. Maybe you fill it to 35 or 40 or whatever, PSI. That's literally that in a square inch of tire space, you've got 35 or 40 pounds of force pushing against it. Any force divided by any area will give you a pressure value. And so what we're doing here is we need to figure out the force, which is going to be the from the weight that we're putting on it being pulled on by gravity. And we need to figure out the area over which that force is being applied. And that's going to be the cross-section, or the diameter of the plunger of the syringe. So they kind of do some of the math for you. They say here, you know, the plunger of the syringe is a circle, area of a circle is pi r squared. They tell us that the syringe that's being used in this experiment is 15 millimeters across. So there's the radius, there's the math. This is the area of that syringe plunger in square meters, okay? So they did that for you. The force, from a physics class, we would learn that force is mass times acceleration. So as we're adding these weights on top of the syringe, we know their mass because they're labeled in kilograms. The acceleration that they're experiencing is just the pull of gravity, the acceleration of gravity, which on Earth is 9.8 meters per second every second. And so when we multiply those together, kilograms of mass times meters per second squared, we get this unit, kilogram meter per second squared. That mess together, kilogram meters on the top, second squared on the bottom, that is a unit of force called a Newton. Not a fig Newton, not a strawberry Newton. This is named after the Isaac Newton. This is a force unit, a Newton. It's the standard unit of force in the international system. A Pascal is a pressure unit that is a Newton of force, 1 Newton of force exerted over 1 square meter of area. And so the units here, Newton per square meter is 1 Pascal of pressure. So if we're keeping track, I can calculate newtons here by taking my mass times 9.8 for the gravity here. Once I have force, I can divide that by area in square meters, which I know right there, and I'm going to get pressure in Pascal units. Okay. So what do we do with all this? Well, here's our table. I'm going to show you what my sample lab looks like in a minute, but here's the table. The table in the lab report doesn't have all this helpful information on it. Actually, I'll just show it to you now. When you go into this, it's going to ask if you're completing it online. You are, and you have to get some sample data here. So you'll click yes and confirm. These are all the measurements you would have taken. Now notice here, all of these are added mass. So there's 0. That's the kind of the resting state. Nothing's changed, just the no mass on top. Then we add 0.2, 0.3, 0.5, 0.6, 0.9. Those are the 5 measurements where you've added mass. Readings 7 through 11 are those where you're now pulling on the syringe. So 0.2, 0.4, 0.6, 0.7, and 0.8, those are the second set of data, okay? You wouldn't know that if you didn't read the PDF, and then you'd be in trouble. Likewise, the table just looks like this. And frankly, if I rolled up on this table, I would say, okay, what's going on? What does this mean? What is volume T? What is all this stuff? It's explained here in the PDF and in the text that was just above this table. So the volume of the syringe would have been the reading that you actually see on the syringe. And they explain in the text that you're going to start with 5 milliliters, which we see here in my sample data. Your sample data may be different, okay? But there's that. And then as we add mass to the top of it and we squish that syringe down, the volume number is going to get smaller and smaller and smaller, right? As the mass increases more and more and more. Now we have to remember that the second set of data is the other way around. So now we're pulling open the syringe. So the volume number gets bigger and bigger and bigger and bigger as I'm adding mass, because now that mass is pulling. It's opening up the syringe, okay? What's volume total? They tell me in the text, the way this thing is set up, if I scroll back to the picture, sorry for the scrolling, but if I scroll back to the picture, I had to clamp this thing to make it sealed, a sealed system. So I'm only dealing with the gas that's inside this container here. And they tell me to put this clamp somewhere where I think there's about 1 extra milliliter from the bottom of the syringe to here. So I don't know. I don't know who did that, why they think that's 1 milliliter, but that's the adjustment we're going to use. And so when we go down to this table in the PDF, it says VT is volume of the syringe plus 1, because we're estimating that 1 extra milliliter. Okay, so if this was 5 to begin with, this number is going to be 6. Now the mass added was given to me in my data. All right, 0 for the first one. That's not super exciting, but then I've got mass numbers down here. Force. Well, you can read through the text in the PDF, or you can use the little shortcut right here. Force equals mass times acceleration of gravity. Column C, so this number, times 9.81 meters per second squared. That's the gravitational acceleration constant. So take this number times 9.81, you get that number. Now it's in force, okay? That's in newtons. Now I want newtons per square meter. So here's my added pressure, newtons, which I had right there, column D, divided by that already calculated for me area of the plunger, 1.77 times 10 to the minus 4 square meters. Now, I would suggest here, perhaps, depending on your calculator or whatever you're using, be very careful about adding in this or putting in the scientific notation correctly, right? You're dividing by a number that's like 0.000177. So the number you get here should be much larger, like 1,000-fold larger number than you had here. Okay, if it's not, you've messed up your scientific notation. Total pressure is pressure in the syringe plus the pressure in the atmosphere. Remember that atmospheric pressure, all that weight of all those gas molecules up above, in this case, your syringe plunger, going all the way up to space, that exerts some pressure. And so we have to remember that that pressure is in there too. So I'm making a relatively small change in that large pressure. And this is where I want to go to the separation here, and they have these bold lines for this reason. In the added mass situation, this formula is correct. You're going to take the pressure in the syringe, which is this number that you've calculated here in column E, and you're going to add that to the atmospheric pressure. We'll get to atmospheric pressure in a second, but you're going to add them together in here. For these other ones, you're reducing the atmospheric pressure by a little bit, right? You have all that gas coming down from space, pressing on your syringe, and you're sucking a little bit of pressure away from it. So down here, samples 7 through 11, you're actually going to have atmospheric pressure minus your calculated pressure in your syringe, okay? Once you have the pressure in column F and you have the volume in column B, we can calculate PV by multiplying them together. Notice our units here are going to be pascals of pressure times milliliters of volume. That's not the most traditional set of units to be using here, but it doesn't matter because we're being consistent. Because Boyle's law is a law, right? It's the way things are, assuming the temperature is constant and assuming your syringe isn't leaking. All of these numbers should be the same. They won't be because it's experimental data and you'll get a little bit of variation. But if one of these numbers looks like remarkably different to the other ones, you probably did the math wrong in that row. Okay, so PV should be a constant. These numbers should all be reasonably close to each other. Okay, and then we'll do some statistics. So what I did, and you don't have to do this, but what I did is I basically recreated this table in Google Sheets because it was a lot of data to write out, and I didn't want to do that, frankly. So I trusted Google to do the math for me instead of me having to do it and risk messing it up. All right, so I just want to scoot that out of the way over there. So for now, PV measurements. In red, this is the data that LabFlow gave me, right? And so I just basically recreated this table in Google Sheets. And then what I did is I used these little, guides, if you will, to do the math in Google Sheets. You can do it on paper with a calculator, it doesn't matter. What I did here, I've got my volume in the syringe was 5. I added 1 to it. In every case, I added 1. That was that dead volume of the clamp, that little tube, right? So that's done. Now my mass added was what they told me in the table. So here I had no added mass, which means I had no added force, which means I had no added pressure, which means that this is atmospheric pressure. Now, where did that number come from? Well, they did tell me in my data up here that the atmospheric pressure measured in inches of mercury was 30.08 in my set of data, 30.08 inches of mercury. You could use the conversions that are way up at the top of this thing, right here, to convert inches of mercury to millimeters of mercury, and then to convert that millimeters of mercury to pascals, right? And that's what I wrote on my Google Sheet here, 30.08 times, that's inches, times 25.4 millimeters of mercury per inch. Those cancel. Millimeters converted here to pascals, and I get 101.862 and change. And since Google was managing, my spreadsheet was managing the decimal places, I just kept them all. Remember, you should keep all the decimal places for these intermediate calculations, and then you would round for significant figures at the end. So having a spreadsheet is great because you don't have to worry about writing out all those numbers. The other way, of course, and this isn't cheating, but I could go up here and say, okay, 3008, Google, why don't you tell me about pascals? Okay. And they tell you for an approximate result, multiply by this number, but there it is, 101.862 and change. That's what I have right here. So however you want to do it, you need to start in pascals because that's what our force unit is going to end up giving us in the later calculations. All right, so basically this is atmospheric pressure. And if I take that atmospheric pressure times this 6 milliliters in volume, I get this number, okay? And that would have units of Pascal milliliters. Now readings 2 through 6, I'm adding mass. And so I separated these out just so I could see them better. The volume calculation we talked about. Here's my added mass. It was 0.15 kilograms. So here, remember on that table in the PDF, it said force is the mass times acceleration of gravity. So on my spreadsheet, column E times 9.81. So this times 9.81 gives me that. Now, pressure in the next column is this force divided by the area of the plunger, which was that 1.77 times 10 to the minus 4 square meters. So I get this number. Remember, this is what I was saying, because you're dividing by a tiny, tiny number to get this, the number here for pressure should be much larger than the number there. Right? So I went from 1.5 to 8,300. That's good. All right, I've got that. Total pressure now, I added this 8,300 pascals of pressure by putting that weight on top. The atmosphere was already giving me 101,000 pascals. So I add those together to get a total here of 110,000 and whatever that number is. And then PV is pressure times volume, okay? I'm gonna do that for reading 3 and 4 and 5 and 6. And notice here that my mass is going up, 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 which means my force is going up, 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 up. My added pressure, my total pressure is going up, 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 up. But the volume is going down, 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 down. And so when I multiply those numbers together, I get PV that should be constant, okay? Now you'll notice looking at these numbers, I started at 611,000, now I've got 650, 660, 680, 713. They're all in the same neighborhood. Even though they're not the same number, they're all in the same scale, right? They're in that 6,500,000 kind of number, okay? So reasonably okay. Now I've separated out readings 7 through 11 because those are subtracting mass. Those are the ones where I have the mass hanging from the syringe. So I did the volume calculation the same way. It's just syringe plus 1 to account for the dead volume. I do the force calculation the same way. Column E here, mass times 9.81. I do the added pressure, except in this case, it's not really added pressure. It's really subtracted pressure, right? And so what I'm doing here is really taking my atmospheric pressure and subtracting this number, okay? So you'll notice that these numbers are kind of on the same scale as those numbers, right? When I added 0.15 kilograms, I had 8,300 here. This is about the same kilograms. I've got kind of sort of almost the same number. So you should see some similarities here. If anything sticks out like a sore thumb, you probably did some math wrong, especially watch that scientific notation in this number here. Total pressure now is a subtraction because I have atmospheric pressure, which was that 101,862 number, but I'm subtracting this little bit of pressure now. So I get these. And notice here, my pressure is going down, 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 down as I pull open that syringe, but my volume is going up, 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 up. And so when I multiply them together, I get reasonably consistent numbers, okay? Now, why are these numbers different to these numbers? Well, there's some mechanics here, right? Pulling on a syringe is a little bit different to pushing on a syringe. And we have to wonder in an experimental setup, are the seals all good and tight? Is everything completely airtight? Is the temperature perfectly the same from measurement to measurement? You know, the way this is set up, we're only measuring the temperature once at the end of the experiment. And generally speaking, if you do it, you know, reasonably quickly, maybe it takes you an hour or two to do all of these measurements, the temperature is probably pretty similar, but it might not be. So anyway, we've calculated a bunch of numbers, and we know that based on Boyle's law, all of these numbers should be the same. And so then we get into the second part of this. We've done the data collection. Now we're going to do a little bit of statistics. This is standard deviation. And unfortunately, at least on my view, the equation isn't here, but I've got that in the spreadsheet. To do standard deviation, you're basically going to take each measurement that you took and calculate how far away from the average of all your measurements that one measurement is. That would be a deviation. That could be positive or negative, depending on whether your one individual measurement is higher or lower than the average, right? Some of them will be higher, some will be lower. So it could be positive or negative. And to get rid of that, we square the number. Because if you remember from your math classes, a negative number times itself or times any other negative number is a positive. So we square it. Well, then we're going to get some sort of squared deviation measure, and that's fine, but it doesn't tell us the whole story because we don't know how big the value is supposed to be. So if my numbers are, have a range of 100,000, maybe that sounds real bad, but if the thing I'm measuring is in the billions, and 100,000 maybe isn't that bad. Now, if the thing I'm measuring is in the thousands, then having a range of 100,000 would be a real bad set of data. So we need to normalize it. And so we're going to do that. And I'm going to show you here. It steps you through this. It also steps through in the PDF down here. And it goes through step by step by step by step. Okay. I'm going to show you how this works on my spreadsheet as well. So first thing they ask you is to calculate the mean value. This is just an average. So add up all of your PV values here and divide by whatever number. There's 11 of them, I guess. So divide by 11, just a standard average. Okay. And then you copy those same values down here in PV value. The deviation is that individual value minus the average that you've calculated. And you'll do that for each one of those. Some will be positive, some will be negative. Some will be large differences, some will be smaller differences, okay? Then the deviation squared is literally this number squared. That number squared. Okay, you're going to square each one. Then they tell you to sum, to add together all of these squared deviations. So everything in this column gets added up to a big number there. Divide it by the number of measurements minus 1. This is a statistical thing, and if you take a stats class, which I highly advise if you're staying in science, you can hear the arguments about why we do this. But since we took 11 measurements, we're going to be dividing by 10. So it's literally that number divided by 10. Then we square root that number. So just hit the old square root number on your calculator. And then that's it. That's our standard deviation, is the square root of the sum of the squared deviations divided by the number of measurements minus 1. Blah. Okay. Here's where I did this in Google Sheets. I took all of those PV numbers. And where are my numbers? They're there. There's the formula. Okay, the sum of the squared deviations divided by n minus 1 square rooted. Okay. And so here's what I did. These are all my individual PV values I just copied from the other table. These are the deviations. So I took that and subtracted the average. And then I took that and I subtracted the average. And I took that and I subtracted the average, right? One after the other. And you'll see some of my values are negative here. Some of my values are positive. Some are quite small, some are larger. I'm going to square each one of those. So that number squared to give that number. Okay, let me make this a little bigger. I apologize. I just looked at my other device and I saw how small this was. There we go. Okay, so I squared each one. On the report, it asked me to add all those together. So I just did a sum of all of those, added them all together to get this great big number. Then I took that number and divided by 10 to get that number. And that was my number of measurements minus 1. Then I took a square root of that number to get 47,000. Okay, that's my standard deviation. 47,000 right there is my standard deviation. So if I were reporting this set of data, like in a paper or at a conference or a presentation, I would say I had 634,955 was my calculated PV value with the standard deviation of 47,000. So that's saying my average is 634,000 and change, and my numbers all kind of fell within 47,000 of that. So that's reasonably okay. It's less than 10%. Most people would say that's reasonably okay. We also like to include a range. And so the last couple of questions on here ask you to do the range, minimum and maximum. Okay. So literally all you're going to do is look at this set of data right here and find the minimum and find the maximum, okay? Sorry, wrong. The range is I had to look at the way this is written. The range is the mean pressure volume number plus or minus the standard deviation. That's what I just said. So 634,000 divided by, let me fix these, answer the question they're asking. I would do my 634,000 average minus my standard deviation, okay? And then I would do the same thing, my average plus my standard deviation. Those would be the numbers I would put in for minimum and maximum. So this is average plus one standard deviation. Oops, average minus one standard deviation. And the maximum is the average plus one standard deviation. Okay. So you'll see numbers expressed that way in papers, in presentations, all sorts of things like that, where having just the average isn't enough. We need some sort of a sense of what kind of environment it's in, what kind of data set it came out of. So oftentimes you'll see something like 634,000 and change plus or minus 47,000 and change written that way. Sometimes you'll see it written as a range. So here's my average, here's my range, one standard deviation either way. So for all the statistical fun, you can get a little taste of it in the PDF. Up here, there was a little section about standard deviation. I would highly encourage you to take a statistics class if you're going to stay in science. There's a whole lot of demand for scientists who understand statistics. So I would suggest you take a stats class if you can during your program. It's really helpful. Once you get those pieces in there, you'll hit submit and you're done. Okay, it's just Boyle's Law this time, just pressure and volume, and that's it.